Hello, everybody. I'm very happy to share this talk with you. My talk is titled Towards Responsible AI. And so let's start by looking at how AI and human work in the past. And this is best summarized in Asimov's 3 laws of robotics. In his 3 laws, the first law states that a robot should never hurt, injure a human being. And the second law says the robot or AI must obey orders given by human, except it must obey the first law. Now, all these laws are designed under the assumption that the robot is on the opposite side of human, and maybe one day will become a super robot and as a result can hurt human. But in fact, this is not how AI should be developed. When we look at today's, starting from AlphaGo and the upsurge of AI development around the world, we see people are excited with not just unmanned vehicles and commercials, but rather AI that can work side by side with human. And this is indeed my point of view. That is, AI needs humans as companions, and in order to do so, AI needs to explain its result to humans, require human debugging, require human supervision, and pay attention to interest of humans. And when we look at interest of human, the first interest is privacy. Privacy is a fundamental interest of human being. And so when we have, especially AI, big data motivated, driven AI algorithms, it's very likely that human privacy secure data is leaked. As a result, it's not straightforward to obey this requirement. And the second one is that AI should be robust and AI models should not be fragile. Instead, it should defend against malicious attacks. And thirdly, AI should make sure humans can understand how it works and how its decisions are made. So this relates to explainability. So let's look at first, AI should protect user privacy. And so, as I mentioned, this is especially driven by today's AI technology, which is, it's a big data-driven AI development. For example, in finance, we try to build a risk model for financial applications such as loan approval process. And in doing so, we need to train the model using historical data. And these may come from a lot of data in micro loans, or very few data in large loans. And no matter what, there's a need to transport the data, to collect the data, and to work on the data. And so there's a lot of chance for privacy leak. There's also important applications in cloud computing setting. For example, in edge devices, in driverless cars, in our iPhones, and so on. Each edge device needs to update its AI model and needs to supply the cloud with new data in order for the model to get updated. Now, in doing so, it's very likely for any edge device to leak its private data, and such data cannot be protected well on the cloud. Okay, so we see the problem with this arising very fast. So for example, in Europe, there's a new law called GDPR, which is introduced to protect the interest of individual and organizations which hold the data. And when companies such as some leading search engine and social media companies violate such laws, they are charged heavily by the law. In China, we also have just introduced a new data security and privacy law, which is under discussion and will be enacted very soon. And such laws are very sweeping in coverage and also very strict. The central theme is to protect the interest of individuals and organizations which are owners of the data. Okay. Now, thus arise new technologies such as multi-party computation and federated learning. In federated learning, the basic idea is to keep the data partitioned while the participants can still collaborate. They collaborate by exchanging parameters through exchanges of local parameters. But such local parameters are protected by encryption. Okay, so the goal is that no local privacy is leaked, and at the same time, a global model is built virtually, and everyone can use the model to benefit its business. So we try to explain to people using a cartoon such as this, and we consider a model similar to a sheep we try to raise, and the grass as the training data. And so when we want to build up the model, the traditional way is to move the grass to a central location where the sheep is. Now, this way violates the privacy protection because the grass secret about each farm is leaked out. Instead, in federated learning, we try to lead the sheep to each farm, so the sheep can keep growing, and the grass, which is the data, does not need to travel outside the perimeter. And all of this are done so that all these participating farms can share the benefit of a grown sheep or a built model. So this is the idea that Google used in its federated average algorithm, where each edge device can build its local model and exchange encrypted parameter with the server. The server's job is to update a global model under encryption, and thus will not learn the privacy of each local model and data. And yet the model can be updated and partition distributed among the edge devices. So this corresponds to a data model where the data is partitioned along the sample dimension, which is horizontally, whereas the each data store can have a common set of features with the others. So they share the features, and yet they don't share samples. Now, a mirror image of this is to have different organizations that share samples but not features. An example of this is two hospitals, where we have one hospital taking maybe CT scans of a patient, and another one takes the DNA test of the same patient. So the samples are exchanged, are shared, but attributes are not shared. By working together, these two hospitals can build a complete picture of the patient. So this is in a system view. This is shown on the right, where we have two servers and they share models by exchanging the parameters. Their model, local partial model, can be built gradually, but the privacy is not leaked. Okay, so in summary, we have these two views. On the left, we have the horizontal view, and on the right, we have the vertical view. On the left, we have a client-server kind of setting. On the right, we have two equal participating party setting. Although this is not a strict partitioning in in business-wise. So when we have two hospitals working together, we can also have a horizontal view, whereas the individuals can also work under a vertical view. Now, so researchers have tried hard to apply each of these views to existing algorithms. Take random forest algorithm XGBoost as an example. We have on the left-hand side, we have a secure boost algorithm, which is to work under the vertical view. And this has been successfully implemented in the open source software platform called Fate. Another one is a horizontal view, which is here worked out by a group of researchers from University of Singapore, National University of Singapore, headed by Professor He, Bingsheng He. And the algorithm is based on GBDT. We try to summarize these data models and these algorithms in our newly published book, Federated Learning, both available in English and in Chinese. And last year, Google led a group of researchers from across the world and across academia and industry in building a white paper. And this white paper is available to report on the latest in federated learning. It's available on arXiv. And since then, there has also been further progress in federated learning. In this work, our researchers try to combine transfer learning with federated learning. So let's say one party, party A, has a lot of data and has a mature model, but party B is new. So party B had faced a cold start problem where it needs to build its data by leveraging knowledge from party A. Now, the traditional way of transfer learning is to ship part of the data or the model from party A to party B, thus violating the privacy of individuals in party A. A new way under federated learning is to let them co-build a model to help party B while protecting the privacy of data in party A. And this is done, for example, in a deep learning setting shown on the bottom, where there is a certain number of layers of parameters in party A that's exchanged with party B under encryption. And the model in party B can thus leverage this very useful pre-built model to grow its own model very fast. One problem we find in this setting is that theoretically it's very appealing, but in practice it's very slow. And so we recently worked on this in a research project and tried to build a batch model. In the batch model, we try to group as much local computation as possible in one go and try to minimize the parameter exchange between the two parties. And it's very effective. In our implementation, we found that the training can be sped up by as much as 100-fold, and the accuracy loss is extremely low. We are also considering building a public data set to promote public domain research on federated learning. And in this website, as shown on the screen, we make available a computer vision problem. And the setting is on safety insurance in different construction sites under surveillance camera. And by building a global virtual model, we try to leverage the data from all parties while protecting their privacy. I should also mention that we are also working very hard on building an international standard, and this one, IEEE standard P3652.1, is first such standard on federated learning. This is especially useful in a business-to-business setting. We are also working with Linux Foundation and GitHub on promoting a public domain federated learning platform, and now it's available on Linux Foundation called FATE. Recently, we have put to use our federated learning platform on various current problems. One such problem is the COVID solution to COVID. In China especially, it's very popular to use a health code, which can communicate with data stores and shows your where you have been in the past 14 days. And that gives the people from various social places or cross-border sites insurance that you are probably healthy, okay, because of social distancing, especially in the low-risk area you have been operating. Now, but this a side effect is this using this code could reveal your private information to others. So using federated learning, we make sure that the data stored at various parties are put to use in building a model, while the data is not shared with others. Especially, this is useful for building a very effective health code without violating any individual's privacy. Okay, so above I have summarized our work in federated learning. Below, I should give an overview of our recent work also in security and explainability. In security, we care about security of a model from various angles. I summarize 3 such angles here. The first one is to protect the privacy of training data. And this is especially when different parties are working together and one party may be interested in learning the privacy of other parties' private data. The second part is to protect the model training so that there is the parameters are not biased towards any particular malicious party. And the third one is privacy is security in the test stage, where a slight change in the test data will not result in a very large change in the prediction. Okay, so I summarize this as 3 quadrants, 3 parts here. One part is called poisoning attack on the training data. The second is adversarial example in the test data. And the third is privacy attack in eavesdropping on the training data. And in this talk, we are going to focus on C, the privacy attack part. In privacy attack, it's possible to happen when we try to make a balance between security and efficiency. When we use encryption systems that are not 100% secure, especially those methods that introduce noise in order to confuse the other parties, such situation leaking of privacy can occur. For example, in differential privacy, people try to use this to ensure a certain degree of protection of private data while 2 parties work together. And when we use this in federated learning, people have shown that it's not 100% foolproof. So for example, in last year's NIPS, Professor Song Han's group have demonstrated a deep leakage attack model, and shows that when we are not very secure in differential privacy, the other party, participating party, can reconstruct the training data of one party. And but this is a double-edged sword. If we introduce too much noise, then the model is not very accurate. Recently, we have worked in WeBank research group on a solution to address this problem, the problem raised by deep leak. In other words, we introduce a adversarial component locally, and by allowing this to shield part of the private data, it can act between the local model and other participating parties. And by engineering the communication carefully, we can ensure that the confusion to the other party, that is the introduction of noise by differential privacy, can achieve its effect. And at the same time, the other party cannot learn the private information, as well as can build an accurate model. Okay, so so we can address the double-edged sword problem. The last part is we are working on a new research direction, which is federated learning that's explainable. Okay, so in explainability, we observe that when we build a machine learning model, we have different parties to explain to. For example, regulators, monitoring parties are interested in knowing how much risk your model has, and whether your model follow the regulation policy. Developers are interested in the model in order to debug it. And the mortgager or the end user are interested in explaining the logic of your final decision, such as a credit denial. Now, algorithm is very important, but we should also gain a mutual understanding in building explainable models. And this is why we are starting a new standard, international standard on explainable AI. And a particular section is explainable federated AI, federated learning. And here on behalf of Dr. Li Xinfan, I invite everybody to join it. So in summary, in this talk, I gave an overview of our work in federated learning. We also gave a very fast overview on how to defend against malicious users, especially privacy leaks. And finally, point out to our current direction in explainability. Thank you very much.